This episode, I'm talking to astronomer Robert Fesen about exploding stars, white dwarfs, and his recent observations of an 850-year-old stellar collision.
I'm Rob Fesen. I'm an emeritus professor at Dartmouth College in New Hampshire. I've worked at various places. I was a postdoc at NASA Goddard Space Flight Center in Greenbelt, Maryland. I got my PhD at the University of Michigan. Then I went on to the University of Colorado before I ended up in Boulder. After that, I went to Dartmouth after that. So I've been doing research in astronomy for over 30 years. I'm now retired in the last few years, but I feel like I'm hardly retired. I'm doing more stuff now than I have while I was teaching, because I have all this free time. Weekends are just another day to work. So, and I've mostly done work on supernova remnants and supernova. I've studied pretty much all the famous remnants in the sky, the young ones, particularly the Crab Nebula, and another famous remnant for at least astronomers is a thing called Cassiopeia, which is only 350 years old. It's the brightest radio object in the sky outside of the galactic center, so it's a easy object to work on. And I've also done things, older remnants, supernova remnants. There's a thing called the Veil Nebula. The Cygnus Loop is what the scientists call it. Veil Nebula is very, very pretty. It's 3 degrees in the sky. It's 6 full moon diameters. It's a favorite target for amateur astronomers. So I've done a lot of work on supernova remnants. And then I've also worked on supernova themselves. I've had some students working on the actual supernova explosions, and we've done some, I consider, pretty important object, the research on those objects that have broken some new ground on that. So I've concentrated on the supernova remnants themselves. After all the flash is gone, okay, what happened? So that's what I've done.
Yeah, certainly. A lot of our readership and our listenership are amateur practical astronomers and astrophotographers. So a lot of those supernova remnants, particularly the Crab Nebula and the Veil Nebula, will be familiar to a lot of our listeners. It brings me on to something. I often wonder how do astronomers get locked into that particular niche? I study supernovae. I study supernova remnants. I study red giants. How do you actually sort of nail down your niche?
Well, it's out of laziness in a way. When you go to graduate school, you end up working with some professor that either is looking for graduate students or does research that you're sort of interested in or sounds interesting. And so you hook up with this person, man or woman, and you work on that topic for 4, 5, 6 years. And when you graduate, you try to get a job basically with other researchers in that field. So you're naturally just channeled into, after you don't go to graduate school thinking, oh, I'll work on this or that. Well, you can if the school has someone that is willing to accept you in their research team in that particular field. And sometimes, it's amazing. You see some people, they go into astronomy, they want to study galaxies and black holes or whatever, and they end up doing something completely different. That if you had told them what they're going to end up doing in astronomy, that's not too exciting. So I worked with a person, Bob Kirshner, famous astronomer, American astronomer, who was at the University of Michigan. And he's a big supernova researcher. And I had dabbled in a few other topics, peculiar stars with chemically peculiar surfaces. And that seemed a little backwaterish. So supernova are much more exciting. They explode. Wow. They're really bright. They're tremendous. A supernova can actually outshine for a few days their entire galaxy that there's the host in. And so that sounded a lot more exciting. So I did that. And then he was working both on supernova and remnants at the time. So I got into the remnant game. Remnants? Why would I study the remnants? Well, remnants are actually quite important because supernova in other galaxies, they're just points of light, whereas remnants that we can see in great detail in our galaxy, you can see the debris from the explosion. And you can't really do that very easily. One of the things I did after graduate school, I worked on following supernova for many years, decades. And at the time I started to do this, this was in the late 80s. No one had actually thought about trying to find supernova that was still visible. They all thought, well, they get bright, then they fade. A couple months later, they get so faint you can't study them anymore. Well, no, actually, some of them, because the shock of the blast goes out and heats up and lights up the gas that's surrounding the progenitor star, the star that blew up, that stays bright too for a while. And so it turned out there were a couple objects. And I remember going to a couple meetings where I showed them, wow, here's what a supernova looks like 10, 15 years after. And they were like, whoa, you can see. Now, not all supernova are still bright after 10 or 15 years, but 2 years ago, 3 years ago, I and a graduate student, we detected an object, the remnant of a supernova that took place in 1941. Whoa, holy moly, that's 80 years. We're not expecting now that, it's sort of a cottage industry to go after these things. It's very hard, and only a few percent, if that, actually show up very late time. But it's supernova can be viewed as environmental impact statements. You have this blast and then the energy goes roaring out, and anything that's surrounding the star, it comes oftentimes for massive stars that blow up, there's mass lost prior to the star blowing up, and that stuff can heat up and light up, and you can see again, not only the debris of the explosion of the exploded star, but they actually now get an idea of what the surroundings of the star was, and hence what the mass loss history of the star. So it's very there's all these little facets. But to answer your question, we get stuck in ruts, and to switch fields is very difficult because you need time to learn that field. So,
but as you say, you haven't stopped even in retirement, and that's sort of, I suppose, the reason that we're speaking today is because of one of your most recent observations, which sort of the discovery sort of centers around white dwarfs, doesn't it? So I thought it'd be interesting to start off the conversation with that, just a sort of description for our listeners. What is a white dwarf?
So stars like our sun, and a little bit heavier, will evolve over billions of years. Our sun is a 4.5 billion year old star, and then about 5 billion years from now, it runs out of energy in the center, and the core collapses a little bit, and that gravitational potential energy of that collapse heats up the outer layers, and the outer layers can expand to phenomenal sizes, and the surface become cooler, and they become redder looking, and these things are called red giants, and really big ones are red supergiants. Okay, so that gas is so far out, if, like in the case of our sun, in about a mere 5 billion years from now, according to the theory, is that the sun outer layers will expand out to past Earth, out past Mars's orbit, maybe out to Jupiter's orbit. That's tremendous distances. And the gas is so far out, it's just gently tugged by the core of the star's gravity. And so in essence, that material is sort of lost by the star. And these things produced what's called planetary nebula. They were found in the late 1800s, and they looked like round objects. They were not planets, but they looked like planets. And so we have this awful name, planetary nebula, gaseous planetaries. Well, wait a minute. They have nothing to do with planets. They have to do with the end stages of stellar evolution. Okay. Well, you've expanded the outer layers of the star and the center of the star. Usually, if it's under 8 times the mass of the sun, the total mass of the original star, the core can't produce any higher amounts of energy by fusion. And so it becomes sort of an inert object. And so what a white dwarf is the core of a red giant or red supergiant that's sitting there just cooling off. And they're very hot. They can start out a few 100,000 degrees Kelvin, and which is double that in Fahrenheit. But so they can start out very hot because you're looking at an exposed core of a star, and they slowly cool off, and they're pretty hot. And when things are pretty hot, they emit so much blue as much as red light, and so they look sort of whitish. And these are small things. They can contain half or similar mass to our sun. The average mass of a white dwarf is and these things are called white dwarfs because they're so small. They're the size of the Earth, but they have the same amount of mass as the sun, roughly. They can be 0.6 times the mass of the sun, or 1 times 10 to the 1 times the mass of the sun. But so they're these things, white dwarfs, and they're just the cooling off embers of the cores of what were previously ordinary stars that expanded into this red giant phase. So that's what a white dwarf is. Simple as that. And they're incredibly dense, very hot, very small, size of the planet Earth, essentially, and literally very, very close to that. And the density is ridiculously high. A spoonful would be many, many thousands of tons. But they're not heating, they're not producing energy anymore. They're just cooling off.
I think with that underlying context and that underlying knowledge, it makes sort of what we're about to discuss even more interesting. I think we should definitely just delve into that. So, what is this observation or this discovery that you've made, and how does it relate to white dwarfs?
Okay, so just stepping back, so I work on supernovas, mostly remnants of supernova, and there's two types or two flavors, if you want to call it that, of why does a star blow up? I mean, really, why does a star suddenly commit suicide? I mean, why does it blow up? You actually blow up a star? A star can blow up? Well, in stars that are more than about 8 times the mass of the sun, there's an energy crisis they come into where they can't produce any more energy in the core than is needed to keep the layers warm enough and push the gas pressure up high enough to keep the outer layers from just collapsing down. And so a star around 8 solar masses or 10 solar masses, 20 solar masses, they run at some point in their lifetime, and it could be a few million years after they form, they run into energy crisis and the core collapses. And during that collapse, by gravitational potential energy, the energy that you get when you drop something in a gravity field, where did that energy to pull it down? That energy goes into pushing the outer layers up. So the core collapse generates this enormous energy explosion. And so it blows most of the star away. And you can get, instead of a white dwarf, you get a neutron star or a black hole. So massive stars, and it's been known for 40 or 50 years, the canonical number, the number everyone uses between turning from a red giant into a white dwarf, just sedately cooling off, to blowing up is around 8 solar masses. All right. The other type of way you can get an exploding star is in that white dwarf. Okay, if a white dwarf has a binary companion, so it's a binary 2 stars, and actually binary stars are actually fairly common. In fact, out of 2/3 of all the stars that you see in the sky are in binary systems. Our sun is sort of an oddball in a way. It's 30% likelihood that we're in a single star system. In Star Wars, there were two setting stars setting in the original Star Wars episode. So binaries could have a white dwarf that was originally a red giant or red supergiant, and you have this other star. Well, that star, they're both born, but the original star, the star that led to the white dwarf, and the other companion star, about the same age. So one star turns into the white dwarf first. Then the other star turns into a red giant second. Well, in the process, all that gas can get collected, gravitationally pulled into the other star, into the white dwarf. Well, it turns out that white dwarfs can't be any mass, any random size and mass. There's a limit to how much mass can be contained in a white dwarf. It's 1.4 times the mass of the sun. Well, what happens if it's more massive than 1.4? It blows up. It blows up for the sort of the same reason that the massive core blows up. So you can get a white dwarf blowing up if you just push a little extra mass at its 1.399 times the mass of the sun. Just throw a little bit more mass in it and then run like hell, because that thing's going to blow up. And and since it's a white dwarf, they don't have a white dwarf. The outer layers of the star, the hydrogen helium rich layers, they're gone. And so what you end up having is a star that blows up that has no hydrogen helium in it, basically, and they're called type 1s. And yes, and then the stars that are massive stars that have plenty of hydrogen in the outer layers, they're called type 2. So there's 1s and 2s. Okay, 1s, no hydrogen; 2s, plenty of hydrogen. The object that I was looking at, I was not expecting to work on this supernova of where both stars in a binary merge together. You can get them to merge. Why would they merge? Why do they just start, leave alone, just merge, orbiting each other, orbiting a center of mass? Well, it turns out gravitation potential can be released from a system, and you can lose that, and these things will slowly spiral in. It doesn't happen overnight. It will take 50 to 60 million years for two white dwarfs that were originally ordinary stars that will merge slowly together. And in the last few moments, there's an explosion goes on. All right. So, okay, some people think that's one way to get a normal, what's called type 1 supernova. You just don't throw a little extra mass on it. You actually take two massive, say half a solar mass white dwarf, two of them, and you merge them together, and you get a type 1 supernova. There's another scenario that when you get them together, if they're massive enough to begin with, like around the mass of the sun, one solar mass, if both of them are one solar masses, they can not destroy themselves completely. You get an explosion. You get it not as bright as a normal one, type 1 supernova, just an ordinary white dwarf blowing up, but you get something that's little less bright, but there's a surviving star, remains of the combined merged stars. All right, so that's the scenario. So what I did, I don't know how much detail you want to go into, but what happened was, it's an interesting short little story, backstory. So amateur astronomers, I've been working with amateurs in the last few years. The equipment that amateurs astrophotographers have these days is just changed dramatically. These new detectors, CMOS detectors, and these beautiful high quality refractor telescopes, and they can take observations, hundreds of observations over a month or so, just because their observatories are remotely controlled. They just type in what objects they want to look at, how many exposures to take. They're asleep. The telescope's operating remotely, automatically. So these amateurs have been taking some images of the sky. So I've been working with them, and they have given me some great, great discoveries. What other amateurs do also is they oftentimes try to find what we talk about as planetary nebula, and they're fun objects to find because they're bright. Emission line source is very bright. The gas glows in the emissions, and one amateur, there's a bunch of amateurs to do this. They search catalogs that are online, and one of the catalogs that a lot of people look at is there's this infrared satellite NASA put up in the early 2000s called WISE. It stands for Wide Field Infrared Survey Explorer. WISE, WISE. And this amateur, his name is Dana Patrick, and he lives in LA. And he like a lot of amateurs, they go out and look at archival data. There's several data sets online, and you can find interesting objects. And when they find something, they name it after themselves. They keep a track. And this normally the routine is you name it after the first two letters of your last name. His name is Patrick, so it's PA. And this one object he saw was his 30th detection was a ring, a donut-shaped emission in the mid-infrared. Way past what we can see with our eye. It's sort of the infrared that you use for sensors for opening and closing doors and whatever, and turning on lights. It's that part of the spectrum. And he sent that discovery off to some astronomers in the United States using telescopes in southern Arizona. And they looked at it, and normally you would see these things bright in emission, and certain filters can concentrate on those emission lines. And they didn't see a damn thing. They took 20-minute exposure and said, there's nothing here. And Dana said, well, wait a minute, there's something there. I see it in the catalog. Why don't you guys try? So the next year they tried with a bigger telescope down in Arizona, a 3.5-meter telescope, took spectrum of it. That's really how you can really study these. You break the light up. You can see where it's emitting the brightest, and you can tell a lot about the properties, how hot the gas is, and what's the chemical makeup. And they didn't say anything. In fact, they didn't even reduce the data. They said that all the normal emissions that normally you see in planetary nebula, the old remains of stars, the gas bags, not there. So they didn't reduce it. Then some amateurs had been communicating with some University of Hong Kong astronomers who often work with planetary discoveries, amateur discoveries, and they have a catalog. They have an online catalog of all these discoveries, known planetary nebula and suspected planetary nebula. And they went out and used a 10-meter telescope. A 10-meter telescope, one of the largest on Earth in Canary Islands, and they took spectrum. They didn't see anything either. They just walked away. They didn't reduce the data either. But planetaries have very hot stars in the center. That's the core of the remaining star, and so they're usually blue hot stars. So some French astronomers also work on planetaries. This is what a lot of amateurs do, and they said there's a blue star in this PA30 object, Patrick number 30 detection, and they took a spectrum with a tiny telescope, an 8-inch telescope. They said, this star is unlike any central star of any planetary nebula we've ever seen. Well, they sent that back to the University of Hong Kong astronomers, and they got, they got all excited. And they went back to look at the data they had taken, but not reduced. They didn't analyze. And they said, whoa, this thing is very interesting. So they started to prepare a paper, but the Russians beat them to it. The Russians used a 6-meter telescope, one of the biggest telescopes Russia has, and they looked at the star. They saw the same infrared WISE catalog object, and they said, let's look at this. And they saw the blue star in the center. They took a spectrum, and they said, man, this thing is bizarre. The star has a wind. Normally, like the sun has a wind of around 300-400 kilometers per second. That's pretty fast wind. That'll blow your hair back. 300-400 kilometers per second. I mean, that's fast. The fastest winds of not so ordinary stars, the fastest stellar winds is what they're called, is a couple thousand kilometers per second. This star in the center of PA30 has a wind of an astounding velocity of 16,000 kilometers per second. Are you kidding me? I mean, 16,000, that's 3 to 4-fold faster than the fastest winds we've ever seen. So something's up here. So when the Hong Kong astronomers went back to look at the data, they said, "Holy cow! This star is amazing, and the nebulosity it's really faint, but it shows up in sulfur emission, and the sulfur emission seems to be expanding the ejecta of what may be a supernova. Gives 1,100 kilometers per second. Well, the Hong Kong astronomers are used to working on planetary nebula, which planetary nebula expand very slowly, 10, 20 kilometers per second, which earthly span, that's outrageous, but for astronomical, that's almost dead slow. Supernova expands 10,000, 15,000 kilometers per second. So when they said 1,100, they said, whoa, that's really fast. And they look back at where PA30 is in the sky. It's just about where in the sky Chinese and Japanese astronomers in late 12th century saw a new star that lasted, they could still see it for almost 6 months. So the Hong Kong astronomers came to the party late, but they said, we've got an interesting object, and it's a remnant from a supernova that the ancients, Chinese and Japanese, the Chinese made 3 recordings of it, and the Japanese said there were 2 separate recorded sightings of the star seen in around where P830 is. It's our current constellation, Cassiopeia. And so anyway, so they published their paper in 2021, 2 years after the Russians found the amazing star. And I had worked on the supernova, another supernova remnant associated with 1181, the late 12th century supernova. And I thought, the Hong Kong astronomers got it all wrong. No, they got it right. So I looked right after their paper came out 2 years ago. I looked at P830. I didn't see a damn thing. Just exactly what happened in 2013 after Pat Schick had found it. I didn't see a damn thing. So I said, but then I read their paper more carefully, and they said they saw sulfur emission. So in October of last year, the end of October, I had some time on a telescope in Arizona, and I tried a couple of my main targets, and they all fizzled out. They turned out not to be very interesting. So I looked at P830, and you see the observation that resulted. That object looks like a fireworks explosion. It is. There are fireworks explosions that are, they go up and they sort of bang and explosion. This is perfectly symmetric, and all more than 100 needle-like filaments coming radially, like spokes of a tire, pointing back, and they point back almost to that crazy super high-speed wind star. That, as I said in the beginning, you can get a merger of 2 white dwarfs that still stays together. There's some remaining stellar remnant or star that remains after after the explosion happens. And so that's why we think it's this other version of a type 1, where white dwarfs are involved, but it's now called a 1AX. There's a history behind why they threw an X at the end. The normal one is a 1A. That's the classic 1A. We thought there was just one. So no, there's 1As and there's 1ABs and all this other stuff, 1ACs. So, but this one, we've only known about this particular subtype of 1s or 1As about 20 years. We don't understand them at all. And there's 5 or 6 different theories of how what actually is exploding and how it does explode. But this is probably a 1AX. So we maybe have a very peculiar one white dwarf blowing up that leaves a remaining stellar object in this nebulosity now that we can really study, instead of in a distant galaxy millions of light years away. Here it's not, relatively speaking, it's in our galaxy, so it's relatively close, so we can really take a look at it. So that's a long discussion right there, but it gives you the flavor of how this discovery came to be. And I just, the paper by the Hong Kong astronomers said, by the way, it's some emission in sulfur. And I thought, well, why isn't anyone taking a picture in sulfur? You couldn't see it in anything else. why don't you just take a sulfur image? And that's what came up. And I took a 10-minute exposure and I said, this thing has detail. This has structure. So that's how it ended up.
I mean, the observation in itself is obviously incredible, and it's obviously really exciting, and the image is absolutely spectacular. But I was wanting to get your sort of views on what are the sort of wider astronomical or cosmological implications of this observation, do you think?
Well, supernova turned out to be very important in general in an astrophysical sense. They're the sites in the universe where you make all the heavy elements in stars that then get spread out into the space. For example, type 1a supernova, the white dwarf, is the standard scenario where you push a white dwarf over its 1.4 solar mass limit. That generates almost a solar mass of iron. In fact, most of the iron in the universe comes out of these explosions of white dwarf that generate so much iron. All the iron that we see in the Earth was generated from previous generations of stars, white dwarf blowing up, that seeded the interstellar medium, the gas in a galaxy, with this products, this pollution, if you want to think of it that way, of heavier elements. And then planets and stars form out of that gas, and that's where all the heavy elements come from. Because, everything started out, we think, with hydrogen and helium, pure hydrogen and helium. Okay, stars make heavy elements. That's how they make energy. But how do you get the heavy elements out of the star? Well, you blow them up. Okay, that's how you get all the carbon and oxygen. The oxygen we breathe, the carbon that makes up hydrocarbons, hydrogen and carbon mixed together in molecules. That's how you get the iron. Type 1 supernova, an ordinary white dwarfs blowing up. So that's the essence of why supernovae are so important. They produce both the massive stars, more than 8 times the mass of the sun, and the white dwarfs blowing up. They enrich the gas of that it's in a galaxy that eventually form new generations of stars and new generations of planets. So that's the importance on a wider scale.
Did you sort of have to do any follow-up observations or sort of further analysis in order to actually conclude that you were seeing what you thought you were seeing?
Yeah. So after I took the images, I had a student at the University from Columbia University in New York City. He happened to be there with me, and we were both excited. We had never seen anything like this. I have never. There's no supernova remnant in our galaxy that look anything like this. Unfortunately, there's another nebulosity that is called the Fireworks Nebula. Looks nothing as good as this. Okay, so the follow-up observation was I took some spectra of the gas. I wanted to see what it looked like. It has no hydrogen and helium. Aha, okay, it's a 1. It's an explosion of a white dwarf, okay. And the fact that you see in this core, on the center of all these spiky filaments pointing back to it, okay, so this looks like what some people think is a 1AX. Okay, great. The spectra showed that it's expanding at 1100 kilometers per second, just exactly what the Hong Kong astronomers finally came out with. Great. They get an age of 990 years, almost 1,000 years. Well, wait a minute. They connected to the 1181. That's 850 years old, roughly speaking. They had an error of 300 years. It could be plus 300, 1,000 years plus 300, so 1,300 years old, or 1,000 minus 300, so 700 years old. So the bracketed the 1181, 850 year old. They made a mistake in the calculation. And when I know how big the object really is, and we now know how far away it is, so you know physically how big it is and how fast the stuff expands, you can determine its age. The age I get is 850 years. And as I wrote in a paper, almost a little too good. The error bar for me is 60 years, plus or minus 60 years. So it sure looks like the 1181 supernova that the Chinese and Japanese saw in early August of 1181 AD. All right, so that's the follow-up. Now, I am trying to, this coming week, next Friday, a week from today, is the deadline for submission of what for proposals to use the James Webb Space Telescope. Well, now the James Webb Space Telescope, this thing was found, remember, in the infrared, in the WISE infrared images that look like a donut. Okay. So we know it's bright in the infrared. Webb Space Telescope is built to do basically infrared imaging and observations. So I and some collaborators are busy writing proposals to observe this object with the Webb Space Telescope. The Webb, now on the ground, the images I took were okay. They're pretty decent images, but the either Hubble or Webb can resolve this thing in tremendous 20 times higher resolution. What will look like blurry images after we look at the James Webb or the Hubble Space Telescope images. I mean, I'm expecting these things to look like spokes, thin needle-like spokes coming out of the source. So we're busy writing that proposal, and so that's the follow-up. And we're going to try to do both Hubble and James Webb Space Telescope images. And we know it's bright in the infrared. So what does it look like in the infrared? How spiky does it look? And the Webb can detect dust. The debris of this exploded merger of two white dwarfs should be very rich in everything but hydrogen helium. Should be rich in carbon and oxygen and magnesium and sulfur and argon and silicon, a lot of heavier elements than hydrogen helium. And so they form dust. Those elements in large quantities can form dust. Okay, that may be the source of the infrared mission that WISE telescope built and launched in the 80s, in the 2000s, early 2000s, saw. So that's the follow-up.
That's so cool. I mean, I wish you well with that proposal, and I would love to see what the Webb follow up is. But I also love thinking back to what those 12th century astronomers must have seen and what they must have thought. I mean, they must have I guess they sort of had no idea what they were looking at, and perhaps wouldn't ancient Chinese astronomers at that time, they might have thought that that's like a harbinger of doom or something, or some sort of astrological
So in China and in Japan, there were court scientists, if you want to call them, court observers of the sky, and it was a risky business back then, being one of those, because if there were comets were portends of doom or success in battle, but you could look at it both ways. These knew what the ancients in the Oriental countries called them were guest stars. They were guests, show up for a little bit, and then they move on. And they were different from comets because comets moved in the sky as they orbited the sun, like the planets. These so-called guest stars would shine bright for a few days and weeks maybe, and then slowly fade, never move in where they were originally seen. So they were different. And the colors of them, so there were general portents of doom and gloom maybe, but the court astronomers had to be careful. If they would sometimes change the color of the guest star to the emperor's favorite color. So it was a good sign in the heavens. The gods were shining down favorably on the emperor. So when we read these accounts, and the star was yellow and then it turned red. Well, we don't know if they were telling the truth or if the emperor didn't like the color blue, but yellow is okay. And so, but yeah, what did they think it was going on? It was a sign from heaven, literally a sign of heaven. And it was easy for them to see these events because to ancients, they spent a lot of time outside. And to them, their TV set, there was the sky. So anything occurred in the sky, they would notice. And the fact this object, just to complete the story, was we now know how far away this P830 nebulosity is. And we know how bright it was based on the general reports from the Chinese and Japanese. And it turns out, just like the 180X supernova are less bright than a normal supernova, this turns out to be also probably less bright. So it fits the picture. So we have a beautiful object that has scientific importance. And then we have this thing connected to history, the Chinese records. So there's this connection of modern astronomers and modern amateur, remember, found this in the sky before the professionals found it. And the professionals couldn't make heads or tails out of it at first. And I got involved because Dana Paczek had asked me to write a proposal last year to look at his nebulosity. And I said, look, there's nothing there. No one can see any damn thing. And he kept pestering me. And I said, leave me alone. There's nothing here. And then I take the picture and I sent it to him, and he was over the moon. He was like, wow, this is great. There's some real interesting structure, and it's going to be important for understanding this particular class of stellar explosions. So there you go.
Yeah, I mean, it's sort of nice that the story came full circle, when you think of sort of the 12th century astronomers looking at it, not knowing what it is, it disappears, and now here we are, with their infrared space telescopes, potentially going to, observe it. I mean, they, 12th century astronomers, if you told them that we were going to do that, it would just be blowing their minds, wouldn't it?
Yes. I mean, and of course they were amateurs too. They were, but they didn't have telescopes. But it's at every level, they were sort of stunned to seeing this new star show up in the sky. It was about as bright as Vega, the star of Vega, a little bit brighter. So it's not quite as bright as the brightest star in the sky, Sirius. But it could have been, close to not quite as bright as Jupiter. Well, you would notice that, and that corresponds to that there were 5 separate records of this thing. And we always had this other object thought to be the remnant of the 1181. I worked on that as part of my PhD thesis, but it never really fit. It seemed older than just 850 years old. It seemed like 2,500 or 3,000 years old. It never fit. It was a shoehorn to try to get it into the 850 year age estimate. This fits without any effort. But it's weird. And you can say, hold on, it's just a strange object. Let's leave it alone. These oddball objects. It turns out, because it's so faint, much fainter than a normal supernova, we don't know how common this is. We would have missed these faint things in other galaxies. And there's some researchers think that 1 of 3 white dwarfs blowing up is this type. It's actually relatively common. We just didn't know it because they're so faint relatively to a normal exploding star.
Absolutely incredible. Yeah, it's so cool. It's such a cool story, and we're sort of running out of time here. But I just wanted to say, thanks for coming on the podcast and sharing this story with us. And who knows, I mean, as I said, I wish you luck with your proposal, and perhaps if you get some observing time, you could come back and tell us what you find with Webb,
Well, I don't think I'll need to come back and tell you, because if I get the time, this will be the Space Telescope Science Institute people have already contacted me and said, if you get some images, if you get the time and you take images, we will show these. These will be in the public domain, public media, because it should be an amazing. It will look better than any fireworks. It'll be quite impressive. So your readers, your listeners should eventually see this. We're hoping that we can get the access to Hubble and the Webb. So
fantastic. Well, thanks again, Rob, for coming on and sharing the story. And best of luck with your proposal.
Yeah, thank you. All right.